Hi, I'm Maroon Thomas. I'm a researcher at Draper Laboratory, and I'm also the chair of the RISC-V software committee. So today I'll be giving a State of the Union talk on the RISC-V software ecosystem. So I'll start off by giving an overview of how our RISC-V software has evolved over the years. Then I'll give a whirlwind tour of the RISC-V software ecosystem. I won't have time to dig into all the details, but I'll point you to other RISC-V Summit talks that do. Then I'll talk about some of the next steps for RISC-V software. So we'll start off by talking about the RISC-V software evolution. So this is Krista Stanovich at the first RISC-V workshop in 2015 in Monterey, California, at the Marriott there. So Krista gave the intro talk there. So RISC-V was just making its way outside of Berkeley, and it was moving towards the RISC-V Foundation to a community project. And so Krista started off by talking about the problems with proprietary ISAs, both the technical and the legal issues. He talked about x86's AAA instruction. He then made the case for open ISAs, and they talked a bit about the history of RISC-V, how it started as a sort of an expedition, a 3-month expedition to find a ISA for research use, and how it eventually broke out of the lab at Berkeley and sort of made its way sort of around the world. And then he went on to unveil the project goal for RISC-V, and that was to become the industry standard ISA for all computing devices. He then dropped the mic and left the podium. Actually, he didn't do that, but it was clear to everyone there that RISC-V was going to be a big deal. It really felt like an important moment in computing history, and so the conference was it was a lot of fun, and kind of got the sense that you were at the ground floor of something big. So Andrew Waterman gave a talk later on that day on the RISC-V software ecosystem, and there was a lot of software that Berkeley developed over the 5 years since the project inception. So there are out-of-tree ports, RISC-V ports for key software packages such as GCC, bin utils, and GDB, and there's also support for LLVM. There were glibc and ulib ports, and there was even a Linux kernel port, so you could run Linux kernel in BusyBox land. There was even an open-embedded Yocto port, so many packages were working there. There's also support for QEMU emulation, so you could run all the software on the QEMU emulator. Berkeley had also developed 2 other simulators. So Spike was the golden model at that time. So it was an instruction set simulator. And there's Angel, which is a simulator written in JavaScript that allowed you to boot an emulated RISC-V CPU in a browser and boot Linux. So there's a screenshot of Angel running here. Angel's now unmaintained, but it was a pretty cool demo at the time. So yeah, the Berkeley folks realized that RISC-V wouldn't be useful without having a good corpus of software. So they put a lot of time into getting this up and running. So fast forward 1 year, in 2016, I gave a RISC-V software ecosystem talk at the 3rd RISC-V workshop. At this point, this workshop was held at the Oracle Auditorium, so a much fancier location and with really fancy catering. RISC-V was starting to grow up. So this is 1 year after Andrew's talk at the first workshop, and it was amazing how much the software stack had progressed. There were community ports for a bunch of different software. So there's a Debian port underway, FreeBSD, NetBSD ports underway, SEL4, Coreboot, uefi were all working on RISC-V support. So it was pretty exciting to see this in just a year's time since Andrew's talk. But there's still many gaps as of 2016 that I identified in my talk. So all the RISC-V software ports were out of tree. So you couldn't just go to kernel.org and grab an image. You had to go to a RISC-V specific port, a repo, and build that port. And often the RISC-V specific forks lagged behind the upstream versions. The privilege specification was still in development at that time, and so this caused Linux distributions and OS support in general to sort of lag a bit and they were all in the pretty early stages at the time. As the privilege spec stabilized, we saw more of the distros and OSs come online. Also in 2016, the developer experience was not ideal. So step one, if you was to build a cross tool chain, you couldn't just grab a shrink wrapped tool chain. You had to clone RISC-V GNU tool chain, and it's take a couple hours to build it depending on your hardware. And the documentation was also lacking at that time, especially for new developers. So fast forward to now, 2020, 5 years after Andrew's talk, and there's been amazing progress in the RISC-V software ecosystem. So the base unprivileged and privileged specifications were ratified in 2019. And as a result, we have upstream support for most open source software. Things really solidified. So we have support for the popular open source tool chains, GCC LVM. QEMU has a really solid emulation for the popular RISC-V platforms. We have distros, Linux distros, Debian, Fedora. You can just grab images off the internet now or from their project pages. And then on the RTOS front, we have FreeRTOS, Zephyr, and many other RTOSs that I'll discuss later on in the talk. And you can now just grab a pre-built toolchain from your Linux distro or a commercial vendor. For Debian users, you can just apt-get across toolchain now, or yum install if you're a Fedora user. And there's more work to do on documentation, but we're making progress. There's the RISC-V Getting Started guide that tells you how to get going with Linux and Zephyr. And there's also the RISC-V Reader book by David Patterson and Andrew Waterman that describes the basics of the RISC-V ISA. And if you want to get deeper, you can get the classic Hennessy and Patterson books, Computer Architecture and Computer Organization, that have been updated for RISC-V. So definitely a lot of progress in the software ecosystem over the last 5 years. So I'll talk a bit about sort of the changing priorities, the RISC-V community. So this is a slide from Chris Stefanovich's keynote at the RISC-V Global Forum. And so he described the goals in 2010 as really the goals of a computer architecture-driven project. So the focus was on architecture and implementations, and to do the evaluation you needed to, there was a need for basic software, but it wasn't really, software was not the focus. In 2020, things have changed. Krista said that RISC-V is now a software-driven project, and the number one goal is to run all software, because if we want to become the industry standard ISA for all computing devices, we need to be able to run all the software that potential users might want to run. So this is sort of a big change for RISC-V. And as we bring up more software, we'll see more uptick in hardware vendors adopting RISC-V and sort of growing the ecosystem as a whole. We have a pretty solid ecosystem of hardware vendors now. There's a number of open source cores, commercial core providers. There's the big announcements of NVIDIA and Western Digital developing cores in-house. But as we build out the software ecosystem more, we'll see more and more people coming to the hardware ecosystem, and that will lead to even more investment in software and on and on. And so I'm really excited to see what happens to the software efforts as some of these new boards come out, like, for instance, the ones from Sci-Fi, Microsemi, Pico Rio, and Open Hardware. So I think we're in for some exciting times ahead. The pace of innovation is definitely accelerating. Okay, so time to get to the whirlwind tour of the RISC-V software ecosystem. I'll move pretty quickly. So there's support for all the open source RISC-V toolchains. So we have GCC bin utils, Clang. There's even support for the formally verified CompCert toolchain. On the commercial side, there's RISC-V toolchains and IDEs from Mentor, IAR, Sager, Green Hills, Ashling, Sci-Fi, Microchip, Andes. There's more that I couldn't fit on the slide. So there's a lot of support there. There's support for various Linux distributions that are upstream. You can just grab images from the respective websites. So there's Debian, Fedora, OpenSUSE. There's a Gen 2 port that's still a bit in the early stages. On the embedded Linux side, there's Buildroot, OpenWRT, and OpenEmbedded Yocto. And these ports have really made a lot of progress. So we can now build 95% of Debian packages on RISC-V. So that's pretty amazing progress in a short amount of time. And we can also now grab pre-built images. You can grab a GNOME desktop image for Fedora. So it's really, the Linux ecosystem is really being fleshed out. So all these ports are for RV64. RV32 is still in progress. Alistair gave a talk at the Linux Plumbers Conference about what's holding up the distros. And what's holding up the distros is a 32-bit glibc port. And so he talks about some of the challenges with getting 32-bit support in glibc, and it has to do with the year 2038 problem. It's actually a pretty interesting talk, so I recommend checking it out. But the good news is that 32-bit glibc should land the next release in a couple months, so then 32-bit distros will come along once that happens. And if you want to dig in more into the to Linux on RISC-V, check out Drew's talk at the summit. On the BSD front, there's upstream support for FreeBSD and NetBSD. FreeBSD was actually one of the first to merge RISC-V support in 11.0. There's also support for the SEL4 microkernel, which is a formally verified microkernel. So they actually have formal proofs for their RISC-V implementation now, which is pretty exciting. If you want to learn more about this, Gernot Heiser is giving a talk at the summit. There's many real-time operating systems that have upstream support for RISC-V now. There's FreeRTOS, Zephyr, RTEMS, NetX on the open source side, and there's VxWorks and PikeOS on the commercial side. So the FreeRTOS is pretty exciting. There used to be 5 different out-of-tree ports of FreeRTOS. Now there's a single canonical port that's being maintained by Amazon. And there's actually Sci5 and Andes have AWS qualified devices for FreeRTOS. So the ecosystem there is really maturing. VxWorks, one of the most popular RTOSs out there, demoed RISC-V support at the last RISC-V summit. And if you want to learn more about Zephyr, definitely check out the keynote talk about building an open edge machine learning ecosystem with RISC-V and Zephyr. The Talk microcontroller operating system, which is an interesting operating system written in Rust and with some interesting security properties, has upstream support for RISC-V. And Alistair is giving a talk about porting Talk to the open Titan root of trust. Finally, XV6, which is an educational operating system kernel from MIT. It's pretty popular. It's used by a number of courses, OS courses. Now targets RISC-V. It used to target x86. And I think this is a pretty cool thing for if you're an OS hacker like myself or into OS history. So XV6 is a re-implementation of Unix v6, which is sort of a hallowed operating system for many. So yeah, lots of progress on the operating system front. So bootloaders and firmware, we have support for the main bootloaders. There's upstream support for grub, U-boot, and core boot now. There's also a legacy Berkeley bootloader from the early days. There's the OpenSBI firmware, which is the open source implementation of the supervisor binary interface. And we also have support for uefi now. And uefi is actually a big deal for server platforms and higher end RISC-V platforms. And so lots of progress there recently. So RISC-V support landed in EDK2, which is an open source uefi implementation, and uefi support was merged during the Linux kernel 5.10 merge window. So that 5.10 should get released in a couple weeks. So we'll actually have uefi support, which is pretty exciting. And if you want to learn more about this, you should check out Atish's talk at the Linux Plumbers Conference. We have simulators and emulators for many different use cases. So there's QEMU, which is one of the most popular emulators, and it has really good support now for the popular RISC-V platforms. There's also Renode, which we discussed in the keynote. There's the Spike, which was the golden model from the early days. So there's Gem5 for architectural researchers, and the TinyEMU, which is taking the role that Angel had, so you can still boot RISC-V. You can still emulate RISC-V in a browser. There's also other simulators like OpenPSim and many others that have imported RISC-V. On the hypervisor front, we have support for KVM and Xvisor, and they support version 0.6.1 of the draft H extension, which is the current version of the hypervisor extension. And you can find more about that in a Noob's talk at the Linux Plumbers Conference. RISC-V now supports the most popular programming languages. We have upstream support recently for Go, Rust, and OCaml. One of the big gaps in the ecosystem was Java, And there's a lot of progress there now. So the PLCT lab at the Chinese Academy of Sciences in Huawei are bringing up an OpenJDK port. Maxine VM was ported to RISC-V. And Chang Jin is giving a talk about the OpenJ9 JDK work that's happening in IBM. So lots of progress on Java as of late. There's also progress on JavaScript, which was another big gap in the ecosystem. PLCT Lab and Huawei again are doing the work here, and they're actually in the process of upstreaming RISC-V patches for the V8 JavaScript engine. And so this is pretty exciting. We can actually have a performant port of Chrome and Node.js now because of the V8 work that they're doing. And if you want to learn more about this, they gave a talk at the RISC-V Global Forum about the V8 work. Okay, so that was the whirlwind tour of the software ecosystem. Now I'll talk about next steps. So to quote Krista, our focus in 2021 is to focus and finish things. We want to push key specifications over the finish line, and we want to have upstream support for these specs as they're ratified. So for the whole software stack, toolchain, operating systems, libraries, application software, etc. And some of the key specs that we want to provide software for: hypervisor, bit manipulation, vector, and crypto. We want to get all of these over the finish line. We also want to define a RISC-V platform standard, so we want to be able to standardize the non-ISA interfaces at the OS hardware boundary, so things like interrupt controllers, cache management, power management, IOMUs, booting. And we have initial target platforms in mind, and so we're starting off with what we're calling the level 0, so the minimal platform for both Unix class embedded systems and Unix class server systems. The embedded systems will come first. And if you want to learn more about the platform work here, there's Al Stone gave a talk at the Plumbers Conference about how to make RISC-V a bit more boring and more standard. And so Al Stone, I should mention, is the chair of the platform committee, and he has a lot of experience with ARM standardization. So we're excited to have him on board driving this effort. So we're filling in the remaining gaps in the RISC-V ecosystem. As I said, V8 and OpenJDK are big gaps that are getting filled now. So we have most of the building blocks in place for our RISC-V software, and so a lot of the focus will be on additional runtimes and software for important application domains and markets that we want to get RISC-V a foothold in. We also want to push towards 100% packages building on Debian and Fedora, so we need to get to the long tail packages, things like Firefox and Haskell, and so we want to make some progress there. And we could definitely use help filling in all these gaps. There's a lot of work to be done. So as I said, most of the building blocks are there now. So there's also a focus on refining the existing RISC-V software, improving performance, code size, and graduating RISC-V software support to tier 1 stable status. So for Debian and Fedora and Rust and Golang and all these things, we want RISC-V support to be as stable and as mature as that of other architectures. Okay, so wrapping up, RISC-V software has grown leaps and bounds in the last 5 years. You can see the RISC-V software list for all the details. It's amazing how much progress we've made in these 5 years. And as Krista said, RISC-V is now a software-driven project. We are working to run all software on RISC-V and to run it well. And this is the only way we can achieve the modest goal of having a RISC-V be the default ISA for all computing devices. Really, we need to bring up all the software to do that. And we need your help building out the software ecosystem. I hope you'll consider joining the RISC-V International Software Committee and the Software Dev mailing list to coordinate on software work. There's a lot of work to be done, and we can use your help. Thank you, and I hope you'll consider joining us in building out the RISC-V software ecosystem so we can achieve the RISC-V's modest goal as the default ISA for all computing systems, computing devices. Thanks.